Welcome to Maths Therapy 101, where we try to solve maths mental problems and, fortunately, end up deteriorating our own mental health. And since suffering alone ain't any fun, so I'm happy to pull you guys into the suffering as well. And before you want to leave this video at this point, I may have to warn you that I have the legal rights to hunt you down till the last breath. So hopefully, you don't decide to do that. So, anyways, the mental problem that maths have is having for this video is a proof to a rather intriguing statement. The proof we need to prove that sum of all integers is equal to 0. Sum of all integers is equal to 0. Now, in mathematics, especially in the field of number theory, we will study in number theory. We have a lot of number sets of numbers which have different properties of their own and contain different numbers. So we know many of them, such as natural numbers, whole numbers, are the ones specified right now: integers, rationals, irrationals, and so on and so forth. For now, we will focus on these three. Now, for natural numbers, it's 1, 2, 3, 4, and so on and so forth till infinity. Whole numbers are like natural numbers only, but we include a 0, 1, 2, 3, 4, and so on and so forth. Now, you may see here natural numbers and whole numbers, they all extend in one direction till infinity, forever and ever. They just keep on increasing and increasing till one direction. So if we would take the sum of these two sets, then it would rather come to be infinity. Same for this too, because it's just increasing in one direction. You don't have anything else to do with it. You just keep on increasing and increasing it, and then adding on and adding on it. You will just get a rather big number, and since we represent big numbers by infinity. But in integers, it's a like opposite situation. Instead of having to increase in one direction, we increase it in two directions. Now remember, the definition of integers is the combination of positive natural numbers such as 1, 2, 3, 4, and so on and so forth. 0, let me get it a bit down. We have 0 and negative counterparts of the positive integers. So by negative counterpart, I mean -1, -2, -3, -4, and so on and so forth till minus infinity. This is positive infinity. Now, when we are trying to add these integers, let me get it back down again. So sum of all integers, let's write it out, integers, it's equal to negative infinity till -3, -2, -1, plus 0, plus 1, plus 2, plus 3, plus till infinity, plus infinity. Now, if we see here, we can group these numbers in some form, such as we can get 0 here, and then we can group 1 and -1, 2 and -2, 3 and -3, 4 and -4, and so on and so forth. We can group every number in it. Now remember the property. When we add a number n and its additive inverse, that is the negative of the number minus n, what do we get? 0. We get 0. And what is this? Number 1 and its additive inverse -1, 0. Number 2 and its additive inverse -2. 0, 3 and its additive inverse minus 3, 0, 4 and its additive inverse minus 4, 0, and this happens for all the succeeding combinations. And since the sum of zero of any number of zeros is just 0, the sum of all integers is 0. But, and now we have just proved it, that sum of all integers is equal to 0. But, okay, sorry for that stutter in the preceding moment. But this proof is rather a baby proof. I mean, like, really small proof. It's for dummies. Like, are you a dummy? No, right? Wait, why did you say yes? Come on, I had such high expectations on you. Okay, you are just a disappointment again. What are you looking at? I'm talking to you. So, anyways, since this is just a very basic proof, I mean, it doesn't has any construct to it. Like your maths teacher gave you some homework and you didn't want to do it, so you just came up with something ridiculous and very small. It's the exact same situation. So what I'm talking about is that we need a rather elegant, a rather professional proof. So for that, we would be dealing with something, a special branch of mathematics. And that branch is called set theory. Sounds familiar, isn't it? Now, I don't need to explain anything about this. I think you already know about it. I suppose you already know about it. If you don't, then just search about it. I have nothing else for you. Now, set theory in alone can't help us prove this because, I mean, what can you, like, the operations on sets are very limited. You have union, you have intersection, you have complement, and I don't remember anything else right now. The operations are rather very limited. You are just dealing with the sets, but not the elements within them. So to do that, we will bring in our special friend over here. That special friend over here is, well, the sigma operator. A familiar guy, isn't it? So in sigma operator, what do you do? Sigma operator is helps us to represent sums of values of functions. So what we do basically do in this, we pick up a iterating variable. So let's just say I'm taking n. We take initial value, starting point. Let's just say I'm taking 0. We will take a ending point. Let's just say it's k, big K, a constant. And then we take an arbitrary function, f of n. What this is equal to is f of 0 plus f of 1 plus f of 3 and so on till f of k. So this is what the sigma operator does. But there is a special type of notation for the sigma operator. It's completely related to sets. It's completely related to sets. So what this is, we will write sigma again, pick a iterating variable, but instead of like picking a starting value and a final value, like specifying a range, I will write belongs and I will pick an arbitrary set A. Yes, arbitrary set A, arbitrary function f of n. Now what does this do? So right over here, this is the special thing. N belongs to A. Now what this does, that it iterates through all the elements lying inside the set A. So let's say I have set A is equal to 1, 2, 3, 4, and till 5. Okay, so this is a set A, and I want to find this sigma n belongs to set A n. So this is basically equal to 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15. What if I want to do this? Sigma n belongs to a n square. This one is equal to 1 square plus 2 square plus 3 square plus 4 square plus 5 square. I'm not going to write the sum. You can do it yourself. So basically what this does is iterate through all the values of the specified set, which is a in this case, and map it to the function we have specified. In this case, it's the function n. In this case, it's the function n squared. And it works for every function we specify. Now, what I want you to notice at is this part. This part. Sigma n, where n belongs to a. Now you might have seen that it just sums up all the elements of this set. Like we have 1 plus 2 plus 3 plus 4 plus 5, which is 15, which is a sum of all the elements lying inside the set A. So basically, this expression right here is used to represent the sum of all elements in the set we have specified. Let me add a page over here. So what the problem we had previously, we need to prove that sum of all integers is equal to 0. We can write it again in the same format we had just seen. So sigma n belongs to integers, n equals to 0. We have to prove this we have to prove this, that sum of all integers is equal to 0. Easy, isn't it? Now, before diving into this problem, we need to address two things. Some notation that I'm going to use throughout this video and any succeeding videos relating to this, and some properties of the special operator we have just derived. So let's get into the notation at first. The first notation I'm going to use is omega n is equal to set n. See over here? Well, what I'm defining is that a singleton set of n is equal to omega n. So omega 0 is equal to a singleton set of 0. Omega 1 is equal to singleton set of 1. Omega pi is equal to the singleton set of pi. And we can do it in nested form also. Omega 0 is equal to the singleton set of 0. Looks good, doesn't it? I mean, you should use a lot of funky math notation anyways. What another notation I'm going to use is f curly braces a set A. Now this is a special notation of function that I'm going to use. Basically, we have a function defined as f of x, and instead of putting a numerical value in this, I'm putting a set A inside, and instead of putting parentheses, I'm putting curly braces. Now what this does, f of curly braces set A, it defines a set n such that f of n and n belongs to, I've written the wrong notation. F of n such that n belongs to A. See right here? So let's take an example of this, such that we have the set A equal to 1, 3, 7. Okay, and the function f of x is equal to x squared. Oops, why am I misclicking? Okay, anyways, so f of curly braces A is equal to, so we have to map it to the function f of n. So 1 square, which is 1, 3 square, which is 9, 7 square, 49. So this is what it is. So we will rewrite the notations we are going to use in this video again. Omega n is equal to a singleton set of n. That looks weird. And f of set A, don't mind my curly braces. I don't know who invented this thing, and it's just impossible to perfect. I've spent like for 25 minutes before. I know. No, wait, not 25 minutes also. Just assume I've spent a lifetime trying to perfect the art of writing curly braces. Still haven't managed to do that. Anyways, so this is f of n such that n belongs to A. So this is a notation number 1, notation number 2. Now we are done with notations. We are going to dive into properties. Properties of the special sigma notation we have just derived. Properties. So we are going to dive into 3 properties, easy to hard. Now the first property states that sigma k belongs to omega n, f of k is equal to f of n. Now this property is easy. Now see, we have omega n. Remember, omega n is a singleton set, meaning it has only one element, meaning that only one element will be passed into the sigma operator, which means that f of n, the single element in the omega n set, will be the only thing returned by the sigma operator. Like if you just add 1, what will you get? You will only get 1. If you add 2, what you will get? You will get 2 only. So if you add only 1 item, you will get that item only. So that's what happens here. For example, let's say I want to do like k belongs to omega 1. Let's just say we have k cubed plus 3. So I'm just going to get 1 cubed plus 3, which is equal to 4. Interesting, isn't it? Another page. Property number 2. So this property means that let's just define 2 arbitrary sets, A, B, are arbitrary sets. Don't mind my handwriting, it's bad, I know it. And f of n, arbitrary function. And remember the second notation I just introduced. Let's just say A is equal to, why A again? A is equal to f of b. So sigma k belongs to A, f, not f, just like k is equal to sigma, let's choose another variable, let's say n belonging to b, f of n. Again, this is straightforward. K is equal to f of A is just basically f of every element in B. So if we add the elements in A, we are going to add elements f of n, f of every element in B. Let's take an example. I'm bad at explaining, I know it, and I stutter a lot. I know it, don't need to tell me anything. So let's say B is equal to 1, 3, 5. Simple example. And f of x is equal to x. X squared is boring. Let's just take what should we take? Let's just take x to the power x. That's it. That's good function, isn't it? So if we want to add all elements, so let's A is equal to f of b. So that means it's equal to x to the power x. So 1 to the power 1, 3 to the power 3, that is 27, 5 to the power 5, which is 3, 1, 2, 5. So if we add all elements of this set A, so sigma k belongs to A k is equal to 1 plus 27 plus 3, 1, 2, 5. Let's get it out. And if we add all if we add n belongings to b, f of n, what do we get? So we first have to add n belongings to b, so 1, f of 1 is equal to 1 to the power 1, which is 1, plus 3, f of 3 is equal to 27, plus 27, 5, and f of 5 is equal to 3, 1, 2, 5. And these both are the same. So our property is being proved by example. Now property 3 is where it gets interesting. It gets really interesting. Let's define three sets: A, B, C. Arbitrary sets. Arbitrary sets. I don't want to write the whole thing. I'm stuttering on the spelling. Okay? A, B, C. Such that A is equal to B union C. B union C. That means I am adding, like I'm combining the sets B and C to get set A. So this works that sigma x belonging to A x is equal to y belonging to B y plus z belonging to C c. But this doesn't work always. It works if and only if the intersection of sets B and C is actually phi, or well, equal to an empty set. Now you may ask me, why is this condition necessary? So let's take an example. Oops, why does that happen? So I'm defining sets B and C such that the intersection is not phi. So I'm going to take set B equals to 1, 2, 3, of course, and C is equal to, well, say 2, 3, 4. So what is A equal to? A is equal to union between B and C, so it's equal to 1. Now remember, set is a collection of elements and it can't have repetitive items. An item can have only one instance of it, only and only one. So if we are trying to union these two sets and the intersection is not an empty set and they have common elements, we have to include these common elements only and only once. So 1, 2, 3. 2 and 3 common elements, we won't include it this time because we have already included them, and 4, it's not common element. Now if we try to add items, like if we try to add all the elements of set A, let's get to a new page. If we let's find them again over here. Or can I just scroll up? Can't I? Yes, I can. So see over here, when we try to add all the elements of set A, so sigma n belonging to A n is equal to 1 plus 2 plus 3 plus 4. And if we try to add all the elements of B and C too as well, let's try another way. Okay, I will just take the same variable because it's not an equation right now. We get 1 plus 2 plus 3, and same for C and belonging to C, and we get 2 plus 3 plus 4. Now notice it right here. We are seeing that in A we are adding the common elements 2 and 3 one time. We are adding 2 and 3 one time. Wait a second, I forgot the spelling of 1 and time. One time. But if we add both of these, we are seeing that we are adding 2 and 3 two times. Why does this happen? Because the sigma operator doesn't know what the intersection of the both sets is. It doesn't know how to exclude them, and it doesn't know what's happening with sets A and B and C. It has been just instructed to iterate through the elements of the sets and add them according to the function. It doesn't know further than that. I mean, it's not sentient to know that. We are sentient enough to know that. So this means that if you're trying to add if we try to add all the elements of set A such that it's equal to B union C and intersection of B and C is not equal to an empty set, we can see that n belonging to A n is less than the sum of these two. Let's try another way. K plus L belonging to C L. See right here, if the intersection is not equal to phi, we are getting a sum of A less than the respective sums of B and C. It's smaller than that, but if we are taking B and C's intersection to be an empty set, A equals to B union C, and B intersecting C is equal to phi, then this doesn't happen. We rather get n belonging to A n is equal to the sum of k belonging to B k plus C plus L belonging to C L. So we have derived the third property with a special condition that the intersection of B and C should be phi. So we have two notations, three properties, and now we can prove our starting statement, the statement by which we have started the video, that sum of all integers is equal to 0. Let's prove this. Proof. Proof. Yeah, let's go. So a set Z, remember its set definition. It's a set, a combination of all the positive integers, negative integers, and 0. So it's defined as this: Z plus union C minus union a singleton set of 0. We just can't add 0 right into it. This doesn't work. So we need to add 0 in a singleton set, and since we know singleton set can be defined by omega, just omega 0. Z plus union Z minus union omega 0. Now let's suppose let set X is equal to union of C plus and Z minus. Let's take it a bit down again. So we get C is equal to X union omega 0. X union omega 0. Now remember, these two sets don't contain 0. And since we are uniting them, we are combining them, so the union will also not contain 0. And since, which is X, and since X won't contain 0, so that means X intersecting omega 0 is equal to an empty set. Great, now remember this. So let's take the summation of both sides. Summation X belonging to C, X is equal to summation Y belonging to X, Y, plus summation Z belonging to omega naught Z. Now remember our first property that we had defined. This will just be 0. No doubt on that, right? Let's add another page. What's up in here? Yep. Now since this is 0, there's no need to write it. Now remember, X is equal to, X is equal to Z plus union Z minus. Now these are positive integers and negative integers. And since positive and negative won't have any overlap, so Z plus intersect Z minus is equal to an empty set. Remember our third property? Let's define it right here. So sigma X belongs to Z is equal to Y belongs to Z plus Y plus C belonging to C minus C. So far. Now remember again, let's take a function. Let f of x is equal to minus x. Now remember c minus is just a negative counterpart of c plus, isn't it? And since f of x equals to x minus, we can say that c minus is actually equal to f of c plus, isn't it? We can say that, right? Can't we? So that means x belonging to c, x is equal to y belonging to z plus y plus c belonging to c plus. And since f of x equal to x, we can write minus c. Now see, we are summing the elements of the same set 2 times in such a way. Okay, wait a second, I forgot to mention one step. Yeah, we need to remember this step. X belonging to z, x is equal to y belonging to z plus. Oh, why did I forget to mention this step? Minus 1 is the constant over here, and constant always gets out of the sigma operator. Wait a second, why z plus belonging to z plus c? Okay, where was I again? Yes. Now we are summing up the elements of the same set. These two sums will be same, won't they be? So when we are subtracting these two same things, when I'm subtracting 1 minus 1, what is it equal to? 0. I have two stones. If I take 2 of them away, how many do you have? You have 0. Why do you have none? I take 2 away, you had already 2 and it's 0. I mean, it's not rocket science, you don't need to apply a hell lot of brain on this. These two are the same sums because we are summing up the same element in both of the sigma operators. And since these two are same, so the subtraction will lead us to, well, 0. What does that mean now? That means x belonging to z. Okay, wait a second. Our starting statement had n belonging to c, n is equal to 0. Wow, that's impressive, isn't it? Like, damn, we have proved that statement. We have proved our statement. So we can proudly say that by set theory that the sum of all integers is equal to 0. And since you have stuck to this part right now, till now, for this whole time, hearing my not so good voice and stuttering and everything else, you have now become a professional. You have now your hands at a professional, elegant proof. Isn't that cool, guys? So well, we have solved one of our friend. Is he a friend or enemy? Frenemy, I suppose. Frenemy maths mental problems and suffered ourselves a lot. If you have any doubts, you can just write that in comments and I will answer that to you. And sorry for all the stuttering and all. I'm just a bit nervous because first time. Anyways, thank you for watching this video. Please give it a like and please subscribe to our channel. We have a lot more coming and I will guarantee you that you enjoy it a lot. Thank you. Have a good day. Goodbye.